Good day, everyone. I'm Marcos Machado. I'm a senior petroleum engineer and senior consultant from Petrobras in Brazil, and I have been spent a period as a visiting researcher in Austin at UT, studying CCS modeling and evaluation in Professor Sefenuri team. My talk will address the topic on a practical and innovative workflow to support large-scale simulation of CCS project. The outline of my presentation will cover introductory topics on CCS trapping mechanism, and I will detail our proposed workflow to model those mechanisms. After the introduction, we will apply it in two different cases, a synthetic one case and a real case model. All the applications will be performed considering a sandstone matrix of the rock. But in our next step, after the conclusion, we will talk about the expansion to a carbonate matrix. As I already mentioned, the scope of this work is to establish a practical and generic workflow for numerical simulation of CCS projects in large field scale models, numerical models, using functionalities available in any commercial simulator package, such as single-phase upscale and dynamic grid refinement. As the main assumptions that we assume in this work, we assume no geomechanic modeling of the structural trap. In other words, no concerns about the CO2 leakage or fault activation. And we assumed an injected stream of 100% of CO2 as well. In this study, we will be concerned with three main mechanisms of CO2 trapping in porous media. The first one is related to the residual gas trapping due to the relative permeability, hysteresis, and capillarity. This graph shows how the relative permeability for CO2 behaves as the CO2 saturation varies. CO2 initially follows the input gas relative permeability drainage curve, increasing its saturation in porous media. With the convection current, CO2 rises, and the water saturation, which decreased initially, now is followed by an increase. Hysteresis of the gas relative permeability curves begins, this point begins the hysteresis and leads to the CO2 trapping. In this example, the CO2 trapped is about 35% in saturation at this point. Another important mechanism is the solubility trapping. The solubility trapping, modeling the CO2 as a soluble component in brine through equations based on the Henry law and through acid reactions to model the CO2 ions like bicarbonate and decarbonate. As you know, that mechanisms is dependent on pressure. There is a positive relationship with the pressure, temperature, negative relationship, and the brine salinity. The solubility of CO2 in water decreases as the increase in the brine salinity. In this graph, the brine salinity is in TDS, total dissolved salts. It's important to point out the mechanism of mineral trapping due to the reactions between the CO2 in aqueous phase and CO2 species as bicarbonate, and the minerals in the rock matrix, such as calcite, for example, that can occur in the matrix or a cementation in sandstone, for example. In this case, it can happen the generation of new minerals like dolomite or the dissolution of the original minerals due to the lower pH generated by the CO2 injection. Now, let's talk about the proposed workflow. As I mentioned before, the mechanisms of CO2 trapping should be considered in the numerical flow modeling of CO2 injection for CCS proposed. Most of those phenomena need to be represented in a fine grid scale suitable to capture accurately their impact on the storage results. However, this level of fine discretization in the entire reservoir or aquifer model can impose numerical issues or prohibitive CPU times. From now, let's propose a practical workflow to simulate CCS large field-scale project to make it possible to model all those mechanisms in a suitable scale to capture their impacts. As a motivation, let's look at how coarse grid scales cannot suitable for CO2 injection because they cannot accurately represent the CO2 plume, as I show in this graph below. This graph in the left side, with a mesh with grid blocks of 250 meters per 250 meters horizontally. And we are comparing this case with a finer grid, refined 5 times the original coarse grid, with in this case in the right side with grid blocks with 50 per 15 meters on horizontally. Although it's evident the necessity to work with a higher grid resolution, the CPU time to simulate this case, the refinement case, reaches 86 hours, considering 40 processors, for only 25 years of simulation. In order to reduce that CPU time, we propose the following workflow. Let's go to the workflow. The first step of this workflow is to simulate the process in a high-resolution submodel or sector model characterized by representative properties of the grid, the full field or the field scale model. This submodel simulation is performed to consider all the mechanisms for CO2 trapping, the solubility, the CO2 trapped as a residual gas, and the mineral reactions. Based on the results that we have in this step, we can rank the most representative mechanisms to select them and consider in the second step only the most relevant mechanisms to simulate. For example, if the rock matrix is a sandstone with lower concentration of reactive minerals, where there is no impact of the mineralization or dissolution reaction over 100 or 1,000 years of simulation, we can follow to the second step without the mineral reaction in the full field and field scale model in this proposed workflow. The following step is to evaluate the application of a single-phase upscaling or single-phase uplating, combining layers, preserving the main petrophysical heterogeneities. And the last step is to adopt a dynamic grid refinement according to the synthetic case results. Therefore, the final model combines selection of relevant mechanisms for full field simulation, numerical upscaling, single phase upscaling, and dynamic grid refinement. Let's look some applications and starting with a synthetic case. To test our proposal, a synthetic heterogeneous model of a saline aquifer was created using a high-resolution grid scale with around 400,000 grid blocks with a size 10 per 10 meters horizontally and 1 meter of thickness. And a single-phase flow upscaling technique was applied to create a coarse grid with only 240 grid blocks with a size of 150 per 150 meters and 80 meters in thickness. One injector is located in the center of those models, inject a cumulative mass of CO2 of 80,000 metric tons during over 5 years. This is around 14% of the total volume, pore volume of the aquifer model. The reservoir rock mineralogy in volumetric fraction was composed of quartz around 30%, K-feldspar around 80%, and plagioclase around 5%, according to this study by Breda. The following minerals reactions were modeled based on the rock mineralogy and this water composition, using kinetics parameters from frequency available in CMG from GEM from CMG compositional simulator. The original pH is around 7 for this case. So let's go to the results. The CPU times are represented in this slide for 105 years of simulation, including 5 years of CO2 injection. The green bars represent the simulation CPU time in a fine grid model. The first bar represents the CPU time of 100 hours when mineral reactions between the CO2 and the rock matrix are considered. If the mineral reactions are neglected, the CPU time reduces to 20 hours, as shown by the second bar. The blue bars represent the simulation in a coarse grid scale. The first one considers the mineral reaction, and the second one without the mineral reactions. Both indicate very small CPU time, but the results are not consistent with the high resolution models, and we'll discuss better later. Therefore, the optimum grid size needs to provide consistent results to the fine grid, but with lower CPU times of the coarse grid model. One approach is to combine both grids, use dynamic grid refinement. Use a fine grid when the fluid saturation changes are high, as represented by the yellow bars. In this case, we have the case with only 5 hours of CPU time in the last yellow bar when mineral reactions are ignored, for example. So the dynamic grid refinement reduces the CPU time by a factor of 4 to 5 compared to the uniform fine grid case. To analyze the results, we compare the three proposed grid scale: fine grid, a coarse grid, and a dynamic grid. We have three graphs in this slide. The graph shows the results for a mass of CO2 as a supercritical non-trapped mobile fluid called free CO2 in this graph, trapped CO2 as a residual gas, and dissolved CO2 in water. The results of a coarse grid are in blue. For a fine grid is in green, and the results for a dynamic grid is in red. During 100 years of simulation, no CO2 mineralization or mineral dissolution was generated. Those graphs bring up how a coarse grid is not adequate to simulate CO2 trapping process in porous media, which misrepresents the unstable flow and channeling. It is observed that the larger pore volume in those grid blocks amplifies the CO2 solubility. We can see this in this graph. The solubility in the coarse grid is higher than in the other grids, smoothing the CO2 plume, as we see before. It occurs due to the larger available volume, water volume per grid block, reducing its occurrence in free and trapped form. So these results show how it's important to work with a fine or a dynamic grid to capture the amounts of CO2 in different forms. In this slide, we can look at the CO2 plume in terms of saturation in different vertical layers, comparing the fine grid and the dynamic grid. And we can see the plume shape is similar in terms of radius and saturation values for both grids, reinforcing these results reinforces the possibility to model CO2 injection using dynamic grid schemes in order to reduce the CPU time. As an example of how the dynamic grid works, this slide shows us the grid refinement following the evolution of the CO2 plume in a cross-sectional view. The CO2 is injected in the bottom layers, and CO2 rises to the top, and the grid refinement follows the CO2 evolution in terms of gas saturation. The validation in a real sandstone aquifer model will be performed as a final test of our proposed methodology. This aquifer is located in the Campos Basin in Brazil. This case is a reservoir sandstone with the sands are composed essentially of quartz and feldspar. The total porosity reaches around 25%, and its original is mainly secondary, generated by matrix contraction, grain dissolution, and or grain fracturing, resulting in an average horizontal permeability around 200 millidarcy. The fluid properties and the rock mineralogy are the same as those used in the synthetic model. The numerical model encompasses a pore volume of 150 billions of cubic meters. The grid block size is around 250 meters per 250 meters horizontally and 10 meters in thickness. The CO2 was evaluated the CO2 injection was evaluated over 5 years in a constant rate of 300,000 metric tons per year through the bottom layers of a vertical injector located at the center of the aquifer. Let's see the results in terms of CPU time during 25 years of simulation, 5 years of CO2 injection, more 20 years. The first 3 blue bars in this slide represent the original grid model with coarse cells, coarse grid blocks with 250 meters per 250 meters, which we know is not adequate to model the mechanisms as discussed previously. The refined model represented by the green bar with an extensive local grid refinement without mineral reactions runs for 86 hours. We can perform a up-layer method in order to reduce the numbers of layers, and the time is reduced to 13 hours. Whereas dynamic grid refinement reduces the times to only 2 hours. With that last version of our model, it takes 20 hours to simulate for 500 years of simulation. So this CPU time shows us that is still possible, still plausible timing for a field project evaluation. Just to compare the results before and after the up layer, this is the results for the bottom hole pressure in the injector well and the flow rate injection of CO2 in metric tons per year. We can see that the bottom hole pressure and the injection rate are favorably comparable between the original and the upper layer model. Just another example of the dynamic grid refinement following the evolution of the CO2 plume, now in a top view. This graph shows us the cumulative CO2 trapped by different mechanisms in percentage over 500 years in a field scale aquifer model, showing the high amount of CO2 in water, as shown in blue. In red is the CO2 trapped as a residual gas by the hysteresis, and in green is the CO2 as a free supercritical fluid. As main conclusion, for CO2 storage simulation, we need to consider the different mechanisms of CO2 trapping in porous media. For that, a consistent grid scale is mandatory for accurate representation of CO2 trapped. The proposed workflow can be applied to reduce the CPU simulation time and keep the accurate representation of the CO2 trapping mechanisms, making possible the simulation of a few field-scale models over several years. We worked with two cases of saline aquifer for this workflow. The CPU time was reduced by more than 95% in both cases. The results preserve the same level of quality in the representation of the CO2 trap mechanisms when the results obtained from the respective final grid scale are taken as reference. As next step, we are now evaluate CCS in carbonate, incorporating new mineral reaction according to the carbonate matrix and the natural fractures, and comparing different approaches to simulate a matrix and fractures, assuming a dual porosity and dual permeability approach, DPDK, classic approach, EDFM approach, and explicit representation of fractures using local grid refinement. So this is my last slide. Thank you for your attention, and I'm now open for a couple of questions.